Okay, I have 1 kilogram air in a piston cylinder. Okay, and it undergoes two processes: constant temperature process, from these, and then a constant volume. So then I want to find the work and heat for each process. Okay, so I have three states. So the first thing I'm going to do is I'm going to go set those states. Okay, and what that means for a closed system like I have here is find the U values again, and I'm doing this for 4A. So let's talk about what I know here. So what I know is P1 is 0.5 megapascals. I know T1 is 227 degrees Celsius. Okay, and I know that V2, well, I'm just trying to figure out, let me put it here. I know that V2 is 2 times V1, right? And that's what it's saying here. It says until the volume is twice the initial volume, okay? So once this gets 2 times as big as that, then I'm good to go. Then I want to do a constant volume heating until pressure is here. So that's 0.5 megapascals. Okay, and then I know that volume, let me see here, I know volume 3 equals volume, 2. Okay, so here's what we got to do. We got to go find my U values. Okay, now here's the other thing. Oh, I guess I should also throw in here the constant temperature. That means T2 also equals 227 degrees. That means I can look up U1 and U2 because for air, if I know the temperature, I know the energy. So 227, okay, notice this is going to be 500 Kelvin, okay, because I add 273 to this, okay. So at 500 Kelvin, my U value is 359.49. That's my U for both states 1 and states 2. Okay? So I get 359.49 right here, as well as right here. Okay? So that gives me my U1, U2. Now, in order to get U3, I need to figure out basically my temperature 3. Okay? In order to find those temperatures at 3, I'm going to use these relationships that I have because I have polytropic relationships here. Okay? Now, this first one is a constant temperature relationship. Okay? Where if you come down here, you'll notice that for isothermal constant temperature, N equals 1 for an ideal gas. Okay? So what I can do is for this first one, which is N equals 1, I can relate P and V using this relationship right here, which is to say P2 over P1 equals V1 over V2. And again, that's because it's a constant. This should be to the N, but N is 1 for a constant temperature process like I have here. All right. So what does that mean exactly? Well, that means that P2 is going to equal P1, which is 0.5, times 1/2. Right? Because this is twice as big as that, which means P2 is 0.25 megapascals. So I'll go ahead and jot that right there. Okay. Now I have the pressure here and the pressure here. Okay. So again, coming back here, this is a constant volume process. You can see for a constant volume process, N essentially equals infinity. Okay. Now if I come down to these equations, these are my these are specifically for ideal gas, but I can relate my temperature to my pressure. Now, if n is infinity, what I have here, instead of n minus 1 over n, I have infinity over infinity, which is 1, which means T2 over T1 equals P2 over P1. Oops. This should be T3 over T2 equals P3 over P2. Because, again, I'm using 2 and 3 instead of 1 and 2 here. So, again, from this, I can say, okay, well, then T3 equals P3 over P2, which is 0.5 over 0.25 times T2, which instead of the 227, I would actually use 500, which means T3 equals 1,000. So if T3 is 1,000 Kelvin, then U3, again, this is for air, so I go back in here, and I go to my air table, A22, and I go to 1,000 degrees Kelvin, which is right here. I can look at my U value, which is 758.94. And that's my U value, 758.94. Now that I have these, I can go ahead and solve these. Okay. Now, again, because this is a polytropic process, because it's constant temperature, and because it's isothermal, which means n equals 1, I can use this equation right here, because this is an ideal gas where n equals 1, where n equals 1 corresponds to a constant temperature. So this is the equation I'm going to use for my work. Okay, so work 1 to 2 then is mRT times the natural log of V2 over V1. Okay, where m is 1 kilogram, r is 8,314 divided by the molecular weight of air, which, for those keeping track at home, that's English. Not that it matters. It'll be the same, but it's 28.97. Because, again, I take r bar and divide it by the molecular weight to get it to r, times the temperature, which, again, is 500 Kelvin, times the natural log of V2 over V1, which is 2. So from that, I can find the work, which is going to be 99.46 kilojoules. Work 2 to 3 is 0. Constant volume tells me that. Okay. Now that I have work and I have all my U values, I'm going to use my first law equation. Delta U is Q minus W. That'll tell me that Q1 to 2 equals 1 kilogram times delta U, which is going to be, well, I'll just write it in there quick. 359 minus 359, because the U's are the same here. Okay, minus 99 plus, because again, I'm bringing that to the other side. Plus 99.46 means Q1 to 2 equals 99.46 kilojoules. And again, that is because at constant temperature, there is no change in internal energy for an ideal gas. Doing the same thing for Q2 to 3, I have 1 kilogram times 758.94 minus 359.49 plus 0, because again, there's no work 2 to 3. So from that, I can calculate that the heat is 399.45 kilojoules. So again, as with all problems, set your states, find your U values. In order to do that, I need to have my T values, so I use these relationships for ideal gas to find those. Once I have all of that, I can calculate my work. Again, this is because it's ideal gas isothermal. This is 0 because it's constant volume. And then once I have my works and my U values over here, I can calculate my heats.